Okay, so that was one reason. One reason is the residual stresses, that we don't follow the same path as shown by this black curve. Okay, the other reason is your initial tolerance, what's called. In other words, your compression member might not always be straight. It might be slightly inclined. Okay, so when you put the load on the slightly inclined compression member, what will happen? That you won't follow this curve. So I mean, like, because of these tolerances and the internal stresses, you normally don't follow exactly this curve, but a curve which is slightly lower than the actual curve. Now, so that's why normally the code of practices, they consider this red curve and they give you the equations corresponding to this red curve. Okay, so they divide the curve in the same way into long column, intermediate and short column in 3 ranges. But they give you equation based on this red curve, which you can see is a parabolic curve. So this is from AISC. These are AISC equations which I have written for you. This is for steel structures. Normally a steel member, if you want to find out the critical load in a column, you follow these equations. Okay, so now what I mean is that the Euler buckling load, that is a sort of a theoretical load, theoretical value. Okay, in reality, in practice, there are other things which makes that Euler buckling load a bit less. Okay, the critical load a bit less than what is predicted by Euler buckling load, and I told you that the reason is residual stresses and the initial tolerances. Okay, so that's why you follow this curve. Now, this is our critical load. Critical load is the critical stress time the gross area. Agreed? So this is critical stress time gross area. That is, you have read it, stress is equal to P by A, P is equal to stress time area. So this is critical stress time area gross area, which gross area means area of the whole cross section. Okay, so this is your critical load. Now this critical stress FCR, this you have to find where you are. Okay, on this curve, are you in the elastic range or are you in the inelastic range, in this range? So that we have to find out. What the code says is that if your L critical or effective length, okay, A by radius of gyration is less than 4.71 square root E by Fy. Okay, E is modulus of Young modulus of elasticity, Fy is the yield strength. Okay, so this is the yield strength of your steel member. Okay, so yield strength can be 36, can be 50, so it depends like what yield strength steel you want to take. It can be 60, so 60 KSI. Okay, so in KSI we are just dealing using US customary rule. So if L critical by the radius of gyration, that is less than this value, then use F critical 0.658 Fy by E. So this value is actually the boundary of the elastic and inelastic buckling. Okay, so this is just the boundary of this value. Now what is L critical? L critical is the effective length. What is the effective length? The effective length means So what we are saying is that the effective length, that is a function of your restraints. Okay? So it is the function of the restraints. If the both ends of the compression member are pinned, then effective factor K is equal to 1. Okay, which means that it will buckle like this. So this is the effective the K value. The length L is equal to actually the length of the column. However, if it is fixed at both ends, this will buckle like this. Okay, because of fixed end, the fixed end won't be allowing this to move. So your K value in this case is half. This is half. And if it is straight like this, one end fixed, another one free, so this is more critical. And the K value in this case is 2. Sorry? Why not? Why not? If your column is freestanding, look at this stand. This is a column and it's freestanding. This is just like this one. It has got the camera load is applied on this column, isn't it? And it is just like this one. So this is possible. Okay, so normally in a structure, I agree that in a building structure it might not be possible, but this can be a column which is supporting something, supporting a headlight or supporting something like that, a board. Okay, so that is this sort of model. So you have to find out the critical length. The critical length is K times L. Okay, and R is the radius of gyration. All the standard cross section have got their own radius of gyration. R is I by A. So now, if your critical buckling length is bigger than 4.71, then F critical is 0.877 times Fe, which is the Euler buckling. Fe is the Euler buckling load. Pi square E divided by KL by R whole square. So I think so you know everything in this. Okay? F critical, as I told you, is the critical stress, and that critical stress is either this one or this one. It depends where abouts are you on this curve. Okay? Are you in the inelastic range or in the elastic range? If you are in an elastic range, then it's 0.658 raised to the power Fy divided by Fe. Fe is the Euler buckling stress, and that is equal to pi square E divided by KL by R whole square. You would know the length, you would know the radius of gyration, K value you would know. Okay, you know, like you might have designed the structure, so you would know beforehand what K value is. E you would know. So I have written for steel it's 29,000 psi. Okay, and you pi square, you know the value. So everything you know in this, you can easily work out your critical load. Okay, do you have any question in this? It's just a refresher. Okay, so this is your Euler, this was your critical load. Now we'll come to our main topic, and which is eccentrically applied load. So this load is not applied in the center. Okay, it is applied off center. So in other words, imagine we have a column. This is an I section column. These are two flanges. You are looking at this column in elevation. Okay? This is an I section. This is an I section. Okay, and this I section, you are looking at it like this. So look, if I look at it from this direction, what happens? I see these two flanges, and this is the web. Okay, and this is supported by 20 kip and a load P kip, which are applied off center. This is a 8 by 28 W section. So your R is 1.62, L is 15 feet. Okay, length is given to you. So this is a column like this one, where load is applied off center. And I gave you the example of this camera and camera stand. The camera is applied slightly off center, which you can see. Okay, this camera is off center from the stand, center. Okay, from the stand center, it is applied at some offset. And similarly over here, we have got two loads which are applied, one at 20 kip, one at 3 inch, and another one at 4 inch from the center. Now, in this one, now we have done from our combined stress knowledge, we know that stress is equal to the strain, the load P by A plus the flexure part, because the off center one will induce stresses in the flexure stresses in the section. So we have done that, combined stress. So this is purely a combined stress problem. Okay, so this is M by S. My by I, isn't it? This is M by S. S is I by C, moment of inertia divided by C, which is the maximum distance of the edge from the center. So S I by C. So now, it's a very straightforward question. We are asked to find out P. We are given this data, a W section which is having radius of gyration, this one, length, this one, area given, Fy is 36 psi, that's the yield strength of this column. I, moment of inertia, is 98 inch 4. We are given depth of this column, so this is the depth. Which is 8.06 inches. So what we have to do is put the values in this equation. So stress we know. But for that, what is P? This equation, so we know stress is known to us, yeah, because stress is this one, 36 psi, it shouldn't go beyond this. Area is known to us, S, which is I by C, that is known to us. Okay, so C is, if this is D by 2, C is D by 2, so that is known to us. So for both of them, we can work out our resultant moment. Okay? So 20 times 3 and 4 times 3. So that is your PE. Okay? So but what is not known to us is the Pn. What P should we use over here? That is not the critical load, is not known to us. So we can the critical load, okay? Because we can't apply straight away this load P. We have to check whether this column is a long column or short column. If we directly apply these loads, what will happen? That will mean that we are considering only compression, that is failing in compression. But we don't know whether it will buckle or it will fail in compression. So for that, we have to go through this exercise. We have to find out what the critical stress is. Okay, that critical stress will, once we find out, we can plug it in here and we can find out our P. Okay, so my point is that although Fy is known to us, okay, we can just close our eyes, put this Fy over here, find out the unknown P. We can do that. But that method, assume that your column is failing only in compression. But we don't know that. So therefore, we can't use stress is equal to Fy. We have to find out this stress from here. Okay? Whereabouts, what is our stress? Critical stress. That. So how can we find it out? First of all, find out L critical by R. So what is L critical by R? Please, can you have your calculators? So L critical by R. So L critical is K times L, assuming that K is equal to 1. Okay? You will be given in the question that whether it's fixed or if nothing is given, you take K is equal to 1. So 1 times L, what is L? 15 into 12, because we have to convert everything in inches, divided by R, and R is 1.62. So what is this?
111 inches.
111. This is L critical by R, so this is unitless. R is also a dimension and this is dimension. Now, let us find 4.71 E by Fy. Because we have to see whether our LE by R, whether we are on this side or that side. So 4.71 E by Fy is equal to 4.71 29,000 divided by Fy, which is 36. So how much is that? 133. Okay. So this is 133. Again, this is dimensionless. Now 111 is less than or bigger than 133. So this is less than 133. That means we are in this range. Okay, which is bigger than 111. So inelastic range. Now, so So our F critical is 0.658 okay, but we need to find out our FE. FE is equal to pi square and that is equal to how much?
23.23.
23 point KSI. So plug it in this one. Fy, which is 36, divided by Fe, which is 23.23. Into Fy again, which is 36, and that is equal to 18.8 psi. Okay, now we can put the value in 1. So we have 18.8 is equal to summation of P by A, which is 20 plus P and A is 8.25 plus I'm assuming clockwise positive. Okay, that's why I've taken this. This will cause clockwise movement, T times 4, and this is counterclockwise movement. So I'm assuming it's positive. Okay, so and you can work out the will come out to be yes. Okay, so that's how you would do your eccentrically loaded columns. Eccentrically loaded columns, they are similar to your ordinary columns. Okay, the method is the same. You follow the same procedure which is this one. But the only difference is that you have this combined stress equation. Okay, you have to use this combined stress equation and work out your stress based on the combined stress. So, this is a typical question. Okay, any question?